G'day, my name is Brendan. This is part 2 of a video on VMStat. Here I'll go through every field of VMStat and attempt to explain them. Just as a bit of background first, VMStat is an older tool and there have been some newer technologies such as ZFS or ZFS that the columns of VMStat don't quite reflect properly or don't really reflect at all. VMStat has always been a little bit tricky to read because it's exposing some of the implementation details of the page-out scanner for system administrators to try and interpret. In fact, when I was a junior system administrator, I was told if you could explain every field of VMStat, that made you a performance expert. I'm going to try to explain every field of VMStat. I'm not sure if that makes you a performance expert because it's actually going through the weeds of some oddities about how these metrics are incremented and where they come from. But it's interesting, so let's go through these anyway. In the first part of this video, I went through 8 columns, so I can skip through those ones quickly. The first one was kthread R, which is the number of threads in the ready-to-run state. I said it's only sampled once a second. You can read the clock routine in the kernel to see that code. That kind of needs to be updated. You will notice that it moves around erratically, and if you want a better way of measuring that, you can try using dtrace and also load averages. B is the number of threads that are blocked on I/O. However, this tends to be not so useful these days. This only really gets incremented by the block I/O routines, such as the ones that UFS will call into. This doesn't really work the way you think it should work for ZFS. So you can have quite a lot of threads that are waiting on ZFS I/O, and it's not showing up here properly. It still can work. And if you had something that was blocked line after line after line for a while, that would be an indication of, usually can be an indication of something is stuck on disk. You should be looking at disk errors. W I did cover in the first part. That was the number of threads that have been swapped out by the swapper, which means the system has been real bad in terms of memory pressure. I talked about these in the first part. That's virtual memory free, and then the operating system's notion of DRAM free. And that's calculated based on free mem. Whether or not this has always been a little bit tricky to interpret over the versions of Solaris, depending on whether it includes the file system cache or not. And that was something that changed between early versions of Solaris and more recently, whether it includes the UFS cache. These days now we have ZFS. It does not include the ZFS cache. So this system can appear to get lower on free memory when it's not so much of a problem, because there's still a lot of memory that's recoverable from the ZFS arc. And you can figure that out by using kstats and looking at arcstats. The other columns we've got, I didn't talk about RE. RE is the number of reclaims. A page being reclaimed is a good thing. It means the operating system needed a page and found it already existed inside the file system cache. Usually this is, we're faulting and we're pulling in executable pages, such as where I run some command and I run it a second time. It's already got those pages still in DRAM. Even though they didn't have an active reference, so they were available to be reused, we were able to reclaim them from the cyclic page cache before they were dropped. MF is minor faults. A minor fault is, you can minor fault for a number of reasons. What most of these will be from is the Solaris demand-based memory system, where as an application, when I ask for memory and I do a malloc, I may malloc a megabyte, but the operating system won't give me a megabyte. It will give me a megabyte of virtual memory. As I access those memory addresses and start to populate them, if there is not a page backing that virtual memory address, it will fault and allocate physical memory at that point in time. That's a minor fault. And so it allocates that megabyte of memory on demand as I actually go and use it. There's a whole bunch of advantages for doing it that way. One of them is performance. You're only doing the memory on demand. It's just a normal, it's normal behavior of the operating system. If you see minor faults, it means processors are consuming memory. Of course, if it gets really large, it might mean processors are burning through memory and growing very quickly. We've got page-ins and page-outs. So a page is an addressable unit of memory, 4 kilobytes or 8 kilobytes, depending on architecture. And page-ins and page-outs are also a normal part of the operating system. I'll page in if I'm reading files from the file system, depending on which file system, and I'll page out if I'm writing them out or if the page scanner is paging them out. ZFS, unfortunately, doesn't update these columns for many of the code paths. So these now are pretty tricky to read if you're on a ZFS-based system. They're tricky to read anyway in terms of there's quite a lot of different reasons why you'll page in and also do page outs. So when I finish these columns, I'll show you VMStat minus P, which actually helps us understand these two guys in a bit more detail. Free is the number of pages that were freed in that interval, and it's another normal functioning part of the operating system. Pages can be freed by the page out scanner, among other code paths. We've got D for deficit. That's abnormal. Deficit comes from the page scanner, and it's part of a clever routine where it tries to predict if there is a burst of memory pressure and the operating system should free up ahead of time and be a little bit predictive. It will bump some counters so that it knows to scan a bit more aggressively. So if you see DE or deficit, it means, what usually means is a process is mallocating and populating memory really fast. And the operating system gets worried and thinks, well, if you're allocating this quickly, I need to make room, I need to make headroom if you're going to continue to allocate and populate so quickly. But again, it's DE and SR come from the old page out scanner, so they're a little old these days. SR is the page out scanner, and as I said in the first part, you'll only see SR if you've exhausted the other mechanisms for freeing memory on Solaris-based systems, which includes eating from the free list, the cache list, reducing the size of the ZFS arc. So if you are in the page scanner, it means there's a lot of memory pressure. And I would be, if I'm consistently in there, it's not just an isolated burst, I would be looking at tuning the applications, identifying who it is, etc. One way of identifying who it is, if you are burning through memory, you'll probably see MF for minor faults, and it's pretty easy to detrace and to see who is doing the minor faults. Disk section has 4 columns for disk devices, and each of these columns is showing IOPS. This is really not a terribly useful part of VMStat, just to look at IOP counts on disks. In fact, due to what's almost certainly a bug, it's showing these as negative 0, if that makes sense. I don't read these. I'll go and use VMStat to find out what the disks are doing. But these are IOPS for those disk devices. And it has a 1-letter code. S means SD. And due to space, trying to stay within 80 characters wide, it's only showing up to 4 disks. Faults has 3 columns in CS, in SY and CS for interrupts, the number of system calls, and the number of context switches. Again, these are fairly normal parts, normal behavior for an operating system. Interrupts, that's how many things work, including network interfaces. When I receive packets, I can be either in interrupt mode or polling mode, not to go into too much detail, but some packets can interrupt the CPUs so that the network device drivers pick them up. System calls, that's how user land processes request the kernel to do work for them, especially I/O related. And if I have I/O heavy applications like, say, Apache that's doing servicing network requests, I'll see a lot of system calls, again, very normal. CS is context switches. And I will context switch when I'm doing I/O and the thread leaves CPU and another thread steps on. If you go back enough decades, context switches were more of a performance problem than they are now, because the cost, in terms of CPU cycles to do a context switch, could start to be a significant portion of the available CPU on a system. These days, context switches are so fast and we have so many CPUs, I tend not to worry about them too much. They're still printed out here, so the number of context switches per second. And these three columns I talked about in the first part, that's user, system, and idle. Those are the 22 standard columns of VMStat. One great thing that was added to the Solaris version of VMStat is VMStat minus P. VMStat minus P splits up the page in, page out, and free columns into three types: executable, anonymous, and file system. So file system pages are things in, say, a UFS file system that have a path, and you're accessing them using open, reads and writes. Completely normal part of the operating system to be doing file system-based page ins and page outs if you're using UFS, or you're using a file system type that bumps these counters. So ZFS does not bump these counters, at least for this version of the operating system and VMStat. I'll skip anonymous. Executable is the number of pages for executable segments. So when I'm loading applications, like I'm typing VMStat at the command line, or if I'm running Perl or Python or whatever, memory is broken up into different address segments. So we have the executable segment, which has the program code, and there will be executable segments for libraries. Generally, you're not going to see too much activity here because if you picture a database that has many gigabytes of files, most of the executable code is going to be loaded, it's going to stay resident in memory when it's the actual file data that's paged in and out. So I don't expect to see much here, but that's the movement of executable pages of memory. I skipped anonymous. That's tricky to explain, but extremely helpful to understand and consider. Anonymous memory is the memory inside a processor's heap. So anonymous memory, to give an example, if I was running a web browser and I'm looking at a page, that page would exist in the processor's heap, which is a region of memory for working data. It doesn't exist on disk. I didn't load that website from the file system. I loaded it from the internet, and it loaded it into my web browser's memory address space. So it's deemed anonymous because there's no file system path to refer to it. If there is memory pressure, what generally happens, and this is why it's really useful to understand the differences here. Let's say I do have my my web browser loaded. As part of my web browser, it has loaded various cached files from disk. So browsers have a file system cache usually. The operating system knows that it read those files from disk and they already exist from disk. So if the page-out scanner is running and it needs to free memory, given a choice between anonymous memory and file system memory, what it will do is it will try to free file system memory first, because you don't need to page it out. You don't need to actually do a physical write of that memory to a disk device. It's already on the disk device. You loaded it from disk. You didn't modify since you loaded it. So it's clean data that was loaded from disk. So the page-out scanner will toss out the file system data first, because if it needs it again, it can just load it back from disk. If pressure gets really bad, that's when it will hit up the anonymous memory areas, so the heap. That's painful because it does have to copy it out. That's when it will copy it out to the physical disk-based swap device, and you'll see your swap device start to rattle. If that's a separate if that's a separate partition, you can often run IStat minus XNZ, and you can see I/O to the physical swap device. If you see API and APO, usually API is a measure of pain, that's anonymous page-ins. So if I'm copying out data from the heap, and the way this page-out scanner works is it is not recently used, and if you read a book like Solaris Internals, it will go into details. It will copy out not recently used pages. If that page is needed again and the application tries to read from it, it will page fault. It will then copy it in from the physical disk-based swap. Often it's a random type of I/O, so it's kind of slow, and you'll see API. So if you see API non-zero and it's consistent, it means not only have you run out of memory such that you've had to scan, but you've also copied out anonymous memory to the physical disk-based swap, and now it's needed again. And the application is being caused pain because it is waiting for those to be copied back in. So this is interesting because it's the closest thing you get to an actual measure of pain. I could scan and toss out not recently used memory that was not used. And I'm not actually hurting anyone. This is definitely hurting someone. Someone wanted that page of memory, now they're waiting for it to come back. That's VMStat minus P. There is another option for VMStat. You can use VMStat minus S and look at the swap in and swap outs, which is the swapper. But that would be, so that's capital S for swap in and swap outs. For you to get to the swapper, you have to be under desperate memory pressure. So, and you'll also see things in the W column. So I would be highly surprised if SI and SO had anything other than a blip for a single line. If you're actually constantly doing swap in and swap outs, you need a lot more DRAM. Or you have runaway processes that are burning up memory. That was VMStat minus P. Now, I've gone through these columns very quickly. What I'd like to do is to really properly understand these, you do need to go through the source code to understand which code paths increment them, which code paths do not. These days with dtrace, there's a great way we can do that. So there is a provider called VMinfo, and what VMinfo gives us is a probe for each of the metrics which VMStat uses, plus more. These metrics are actually, they're in a facility called KStat for kernel statistics, and that's what VMStat is reading to provide those summaries. Dtrace lets us probe when they fire. So we can get all sorts of interesting information like the kernel code path that fired that statistic or incremented that statistic, as well as if that statistic is synchronous with the application, we can find out who it was. Just as an example of this, what I'll do is I'll dtrace and I will look at all the probes, and you don't need to know too much dtrace, but I'm frequency counting the name of the probe and also the kernel stack backtrace. And I'm running this on the system. I'll let it run for a few seconds while it's gathering this, and then Control-C. And so what that's printed out is, this is the statistic name. So I've got AS fault for address space fault. And I can see the kernel code path that led there. So that was a normal path going into trap and page fault. ZFOD for zero fill on demand, address space fault into segvn. Copy on write fault with the code path. Here's a page reclaim, and we can see that came out of UFS get page. Page lookup, found it already existed. We bumped that counter. More page reclaims. Here there's a page out. Pages paged out as well as page out. File system free, executable page out, and so on. These are extremely useful because I can take any of the statistics. Let's say I wanted to understand more about file system page out. I can take any of these stack backtraces. I can read up the stack backtrace to see the ancestry of how we were bumping that statistic. I can look up this function in the source code if it's available and read the point that increments that counter. I do this quite a lot so that I can understand what these metrics mean. VMStat is pretty good. There are a lot of tools out there that are more buggy than VMStat, but from time to time you'll have counters that are simply wrong. With VMStat, it's not generally the bugs, it's just the age of VMStat that hurts us because it doesn't include some of the more modern features like ZFS. So that's a rundown on all the fields. I hope that's been helpful. And of course, you can use dtrace. You can find the code paths that increment these counters so that you can do your own reading to understand them in more detail. Thank you.